In this video, we want to discuss how one can approximate measurable functions with continuous functions with compact support. So let's start first with a remark, with something that we already saw, and this could be seen as the first step of an approximation. So let's recall these facts. So first, if we have mu a Borel measure, this regular and finite on compact sets, finite compact sets measure, then the continuously supported functions, so say measure on a space E, then the continuously compactly supported measure functions, or maybe the set of continuously compactly supported functions with the note C0 is continuous. With compact support, we put a C at the bottom. This space is dense in the LP space for all P equal between 1 and infinity, and not, it's important, P is not infinity. Okay. All right, this is the first fact that I want to recall. Now let me recall the second fact. We're going to use it soon. So if we fix a measure mu, and then if we have a sequence of functions converging in L1, then they converge in measure. Three, if you have a sequence converging to some other function in measure, respect to the measure mu, then up to choosing there exists some subsequence that converge mu almost everywhere. Okay, so let's recall these two facts because we are going to use them soon. We're going to prove this theorem due to Egoroff, which is saying that if you have converging almost everywhere, we may not have converging uniformly, but on a big set you have. So this is important, otherwise not true, under the assumption that the whole space has finite measure. So suppose you have finite measure, suppose you have functions f and f1 and f2, so on, from E into R measurable. If the sequence Fn converge to F mu almost everywhere, then for all epsilon, positive epsilon, there exists a set in the sigma algebra for this measure, such that the measure of the complement of the set is small, so less than epsilon, so A is almost all the space, and Fn converge to F uniformly on A. So means that for any epsilon prime, let's call it epsilon prime, if n is greater than some n bar, then the distance between fnx and f of x is smaller than epsilon prime as long as x is in the set A. Okay, so let's prove this theorem. Proof. So up to changing the sequence fn on negligible sets, we may assume that that fn converges to f everywhere. So they converge almost everywhere, and there's this set of measured zero outside of which you have convergence. Just redefine the function to be zero on that set, for example. Now, what we do is the following. For all k and n, we define the following sets. So is enk to be the union, and m goes from n to infinity, of the x in the space for which the so all the functions of m with m larger than n, their value at x is distance from f of x for less than 1 over k. Okay, now these sets belong to the sigma algebra because the functions are measurable. And moreover, for any k fixed, enk decreases because you're taking n larger and larger, so a smaller and smaller union, so it decreases, and it decreases to what is to the intersection of all these sets. And this set, since the convergence is everywhere, is the empty set. Maybe let's call it with another index. So n goes to infinity. Okay. Now, so these sets converge to the empty set. Now, it's important that the space has finite measure, and therefore we have the limit of these measures, of the measure of these sets, converge to the measure of this set. So we have that, so we deduce that the measure of enk goes to 0, the measure of the empty set, as n goes to infinity. Okay, so what we can do, we can choose some k. So for any k, choose nk such that the measure of the set and of nk is less than epsilon. Actually, let's put epsilon over 2 to the k, so then we can sum it up. Okay, so now let's consider the union of all these sets. Okay, so we let A to be, actually, okay, let's consider A is going to be the complement of the union. E and K complement. Then what you have, the measure of the complement of the set, namely this one, is bounded by the union, by the series of the sum of these elements, and it's summed to at most epsilon. Okay, now for all x in A, we get that the fn x minus fx, this is less than 1 over k by the definition for all n greater than nk. And actually this is in this nk is actually independent on a, so it's better to put the quantifier later for any x in a. So let's delete this, okay, to make it look like this is exactly a uniform convergence. So what we proved, that fn restricted to a converge to f restricted to a uniformly. And the proof of Egoroff theorem is finished. Now let's go in the direction of approximating functions with continuous compactly supported functions. And again, I recalled what I already said. C0 compactly supported E. This is dense in LP for p different than infinity. And I remind you that this was a consequence of Urison lemma. Now we're going to prove a kind of different approximation. That is, again, is an approximation, precise approximation pointwise, but on a almost full measure. So this following theorem is due to Lusin, and this is the statement. Okay, again we have a Borel regular finite on compact measure on E, and we have a function from E to R measurable. There are no there is one assumption on F apart from being measured, that outside the finite set of finite measure it is 0. So let's assume that there exists a set X such that F on the complementary of this X is constantly equal to 0, and the measure of this set is finite. Then we're going to prove that for all epsilon there exists a function that is continuous with compact support, and there exists a set A, sigma algebra, such that first the measure of the complement of the set is less than epsilon, and the function f restricted to A coincide with the function phi restricted to A. And let me write one more property. Moreover, phi can be chosen so that the maximum supernorm of phi is equal to the supernorm of f, where of course, like, I mean, this is or less or equal. Now if f is not bounded, then if this is infinite, then there's no extra statement in this theorem. Okay, but if f is bounded, f could be chosen with the same bound. Okay, let's prove the theorem. Okay, proof. Now let's first consider the case where f is bounded. Okay, let's first. So if f is bounded, I can bound the L1 norm of f. So this is the integral of the norm of f, and I can bound it as the integral of, so I can integrate the sup of f just over the set x where the function is non-zero, right? So I can bound this times the measure of x, which is finite. So what we have is that f is in L1. Okay. Since it's in L1, we can use the density of C0 compactly supported. So we have that there exists a sequence compactly supported such that the sequence converge in L1 to f. Since they converge in L1, as we said at the beginning of the video, we have convergence in measure, and therefore up to a subsequence. I will not write the subsequence, I will still use the same gn. We have that gn converge mu almost everywhere to f. Okay. Next we apply Egoroff, and we get that okay, for any epsilon there exists a such that the measure of the complement of a is less than epsilon, and gn converge uniformly to f when restricted to a. Okay. Now let's remember that we have some assumption on mu. Mu is, in particular, it's regular. And this tells us that we can, so x is an arbitrary set, but we can choose another set that now it's open and contains x, and is with almost the same measure. So in particular, since the only property of x was that, okay, we can, of course, we can enlarge x in such a way that the complement is smaller, and we, as soon as the measure is almost the same, it's going to be still finite. So up to changing x, enlarging a little bit, we can assume that x is open. Okay, so we may assume x open. And now, again, up to taking a subset of k, we can assume that it is compact and has almost the same measure, which means that the complement is going to be a little bit bigger, but still as close as epsilon as we want. And since it's a smaller set, we still are going to have uniform convergence. So I will just say that up to changing a with a compact set that is almost approximating a, we can assume that a is compact. Okay. So now, since now Gn restricted to this compact set converge to f uniformly, now we have continuous functions on compact sets converging to uniformly, then the limit is continuous. So it's a continuous function on A. Continuous, let's say, on as a function, in parentheses, as a function on A. Okay. Now, when you have a continuous function on a compact set, you can always extend it as a continuous function on the whole space. Okay, maybe did here as a I check this. It's more of a topological problem that there exists, since A is compact. So since A, let's also write it here with A compact. Since A is compact, there exists a continuous extension, let's call it F tilde, of F restricted to A. And actually, we can even take F tilde with compact support, because outside of a set of this set X, the function was constantly equal to 0 outside this set. So we can take F continuous with compact support, such that restricted to A is equal to F restricted to A. And we can also assume that the support of F tilde is inside the same open set X. Then I'm going to claim that, so okay, now we consider these two functions, F and F tilde. So let's look at all those points where F of X is different than F tilde of X. Now, this set should be definitely in X, because both of them outside of X are 0, but they're not in A, because A coincide. And this last set, and the measure of X minus A is, let's calculate. So the measure of X minus A is, okay, this is less than the measure of E minus A. In other words, this is the complement of A, which is less than epsilon. Okay, so we found a continuous function that is coinciding with F in this, on this set A, and the complement of A as measured 0 epsilon. Let's prove now. So we proved the first part of the theorem in the case when F is bounded, but let's also prove this last property here. Okay, we might need to change the function F tilde in the following way. So let beta function from R to R whose graph is, okay, I'll draw the graph instead of the formulas. Okay, so it's going to be like this. The function is the identity up to the point where you have the subnorm of F, and after that it is constantly equal to the subnorm of F. In a negative, right, so at the point minus the constant, the subnorm of F is constant. Okay, and now what we are going to do, we let phi to be beta compose F tilde. In other words, what we are doing is we have this F tilde that we like, and then if F tilde is going to exceed this function, we just make it flat in that part, which, right? And you see, this is a continuous function, so this is a composition of continuous function. Moreover, wherever F tilde was 0, this is going to be still 0, right? Beta of 0 is 0. So this is 0, 0. So what we have that this function is continuous with compact support, and whenever f tilde was smaller than the norm, is going to be still equal to the same value. So, and therefore we have that phi restricted to A is equal to f tilde restricted to A is equal to f restricted to A. Okay, and again, as we said, the complement of A as or no, we should not put A tilde. Maybe it's better to put A tilde here, where A tilde is the set X minus A, which is the set here, whose complement is small. Okay. So we proved the case. We solved the case when F was bounded. Now, quickly, what do we do when F is not bounded? When F is not bounded, okay, we just split the space and the function, considering going back to the bounded case. So quickly, we do like this. So we set xn to be all those points in E, such that f of x in norm is less than n, such a way that xn, they are getting larger and larger. They converge to x in E, for which f of x is different than 0. Let's call this x infinity, right? And this was containing this open set where we know that the support of x lives. Now, we are assuming that this set is finite. X is still finite, as a finite measure. Then, again, we know that the measure of x infinity minus xn goes to 0. So one then considers the function g, that is f times the characteristic of this set xn, with n such that mu of xn of x infinity minus xn smaller than epsilon. Okay, on this set, so this function here, so on xn, f is bounded by n, and therefore what we have is that g is bounded. And therefore we can apply the first case of the proof to G to find phi. And this function phi works for f works for f as well, up to an extra set of epsilon measure. In other words, we have to remove this part here, right? But it's a small measure, and then apart from that, we can just approximate f, which in this complement of this set, which is xn, coincide with f, right? So we have found our good phi, which works in a large set. This is the end of the proof of Lusin theorem.